And I want to continue that discussion today. Let me get my. Again, I want to take my time through these concepts because one, they're important. We're going to use them in every application of this class. It'll take a little bit of time. Now it doesn't seem like we're quite getting to chemistry yet, but it's going to pay off. We're not too far from the end. The first couple of postulates are kind of the most important ones. And once you understand what a wave function is and what a measurement is and an operator, then the rest kind of are straightforward. So let's go back to where we were. Let me pull my notes. Okay, so remember from last class, let's just summarize. We had postulate 1, the wave function. And I spent a long time last class convincing you why it may be appropriate to think of systems not as a vector necessarily, but as a function. Right? We looked at position, for instance, right? Thought about our little detectors, and we said, well, if we have 10 detectors in our box, maybe it's useful to think about the system as a vector, because there's only 10 positions that it can be at, so we have a 10 component vector. And each one of those components tell us something about the probability of finding an electron at that point. But we realized that, again, 10 detectors gives us the gaps in the box, and so we want to add more detectors, and eventually we add infinite detectors. And so we have an infinite vector, infinitely long vector of infinite components, and that's just a function. A vector and a function really aren't that much different. It's just that a function is a vector with infinite components. That's not, a mathematician would kill me for saying that, but we'll just leave with it, right? So the wave function, every system can be described by a wave function psi, and that's a function of position, which I call r, x, y, z, depending on what our system is, and time, right? Position and time. Right? And it has some properties. One, psi is complex. So we can define a complex conjugate, which is psi star or psi dagger, however you want to call it, is the complex conjugate. Where psi star inverts all complex values from positive to negative or negative to positive. From plus I to minus I. All right, so an example, just a reminder, and we're going to see why this example is relevant today. If we have a wave function, which in position, I'm just going to get rid of time, is some number a, e to the ikx, then psi star of x is e to the minus ikx. And we discussed a little bit about why this is. Again, remember what this means. Ikx is motion on a circle in the complex plane, right? So this is just an object that's moving in a circle as it's propagating through space. Right? So this object then has some momentum, just moving along just fine. You can think of it just moving, and it's also has some oscillatory phase behavior to it. It's like a wave, right? I think we kind of talked about this. The particle, if this is an electron or an atom kind of floating around in this box. The idea is let me just write this out. This is the same as A times cosine kx plus I sine kx. Right, so you have this particle that's in the box, position x, and and it has some, as it moves through the box, as it propagates through the box, it's also oscillating through some sort of phase, like a wave. Right? And the idea is that this wave is just like an electromagnetic wave, right? Just like light. It has two components. Right? You can see that, right? There's a component, a real component, cosine, and there's an imaginary component which is perpendicular to it. The real is on this axis, imaginary is on this axis, they're perpendicular to each other. That's also oscillatory. So it's got two components that are perpendicular. So this is the real part and the imaginary part. And they're perpendicular to each other. This is the perpendicular sign. They're normal to each other, right? They sit like this, right? Perpendicular to each other. So what does that mean? Right? How do we visualize that? Well, let's think about it like waves. Let's think about like a wave, okay? So let's pretend we have a box of water, okay? And we create a wave in that water, okay? It's got some, like a wave pool, right? Like a wave pool. Right? What happens when we create a wave in a wave pool? Well, a wave starts to propagate like this across the box. I'm assuming the box is the size of this room. And it has the oscillatory component, right? The amplitude going up and down, the ebb and flow of the wave is in the same direction as the propagation. Right? So as the wave moves in this direction, it's just doing this, right? It's moving up and down in height as it moves from one side of the box to the other. Right? So we call that a longitudinal wave, right? The oscillation is moving longitudinal with the direction of the motion. Right? So the oscillations are, you can kind of think of it as like, if this line right here is where the wave is propagating, the oscillations are on that plane. If you think about this as a wall that's raised up, the oscillations are on the plane of that wall, right? Moving like this. We call that a longitudinal wave. Right, so there's some longitudinal oscillation, like a water wave. Right, the idea is that you have some motion in this direction. And the wave is propagating along and oscillating along that vector, right? Just like a water wave. But what's the imaginary component? Well, it's perpendicular to it. Okay, so if we have a wave moving in this direction, and we have a perpendicular oscillation, that means that there's an oscillation in and out of that plane. Right? So as the system is oscillating like this, it's also oscillating in a perpendicular plane, perpendicular to its motion. Right? So there's a longitudinal one where it's going like this, but there's also a transverse component of the wave that's moving perpendicular to that. Right? So it's kind of hard to see that in your head. Let me see if I can find a good animation of it. Right? So this is what we call a transverse wave. And I'll draw it in green. The idea is that the transverse wave propagates, has a phase in the opposite direction, or sorry, in the perpendicular direction. So that's not like perpendicular, right? So that's not like a water wave. A water wave is only longitudinal. Water waves don't compress the water from in the perpendicular direction. They compress and expand the water along the direction of the motion, not this way. But there is something in real life that does have transverse waves, and that's an earthquake. So an earthquake, of course, has this undulation. Right? An earthquake is generally spherically symmetric. So as you move away from the epicenter, there's a propagation of the earth rising and falling like this, like a water wave. But there's also a shear wave that causes the earth to move like this instead. Right? So you have it undulating up and down, but it's also shearing in this direction, perpendicular to that. And that's what really causes the damage. In earthquakes, it's not this. I mean, it does, if the amplitude is big enough, it does suck. If the earth is moving like a water wave, it's not good. But what really kills buildings is that transverse wave. The fact that the system, the earth is not only undulating in this direction, but it's also undulating in the direction along the earth, like this. So that means that this part of the earth may be moving like this, as this part of the earth moves like this, right? It shears, the shearing force that happens in the plane of the earth, and that's what really kills buildings. Right, so it's a lot like an earthquake, but a longitudinal and transverse part. Electric fields, light works exactly the same way. Light, you have two fields. You have the electric field, which is moving like this, along the path of the light. You have a laser beam moving along this direction. You have an electric field oscillating this way, and then you have your magnetic field of the wave oscillating in this direction. That magnetic field is perpendicular to the electric field. So you have a transverse magnetic wave. Okay. All particles have this capability. Right. So, and again, I haven't specified what the particle is. It doesn't matter. It's some particle that has some velocity or some energy that's related to K. We'll look at what that K is in a second, just a number. But we'll see that this is just related to how much energy it has. So there's nothing specifying in particular what this particle is. It could be a particle of light, it could be an electron, it could be an atom, it could be a molecule. It doesn't matter. The fact of the matter is regardless, they act like waves. So particles, all particles or objects, quantum objects, act like waves with two components. Right. That's pretty cool. We'll look at some examples. We'll look at the consequence of this today. Not quite there yet. All right, and they had one more property that we need to remember. So remember, if psi is a vector, it's length 1. And for a function, it satisfies a specific property, which is the equivalent of length 1, but just in function form. It satisfies that the integral over the space of your box, right, whatever the system is in, a box of some sort, we just call this all space, of the wave function's complex conjugate, which is just a function of, let's say, r and t, times the wave function itself, dr, whatever r is equal to 1. Right? So what does it say? Well, it says basically, right, imagine the function's real. There's no complex numbers. There's no complex numbers. These are the same function. Because remember, complex conjugate only flips the i's. There's no i's, it doesn't do anything. So we have, if it's a vector, the vector is length 1. And if it's a function, then the integral over the entire box that you're looking at, and we have to define what the box is, of course, and we'll do that in every problem. Find over the integral over the entire box of the system, the wave function squared. This is just psi times psi. It's real, this is the same. Psi squared integrated over the entire box is 1. The integral has to come to 1. And this has some important qualities. So this is what's called the normalization condition. Again, this is probably just review from last class, but just to make sure. And these have some consequences. The consequences are, well, first of all, the integral of the square of the function over the entire box has to be less than infinity, right? Has to be a convergent integral. That's all it's saying, is that it comes to a number when you integrate the square. That's good. So it has to be less than infinity. But you also have to be able to integrate it over the entire box. So that must mean, that gives a very important condition. The wave function, psi, must be smooth and continuous across the entire region, entire box. All right. This really limits the appropriate functions we can choose to represent a system. Right? It has to be smooth and continuous. What does that mean? There's no jumps in it. All right. So let me just give you an example. So let me just draw some for you, for instance, of what these wave functions might look like. Imagine that this is our box that we put our wave function in, or our system in, and we want to calculate the wave function for it. The wave function has to be smooth and it has to integrate to 0 or to 1. It has to integrate to a number. Okay, so maybe we have a function that looks like this. Something like that over the box. Imagine this was our potential wave function. So examples. Right, well, this is good. This is okay. And why is it okay? Well, first of all, it's smooth. There's no jagged edges or anything. It's just a smoothly varying continuous function. And if we can think about it, it looks like it integrates to a specific finite value inside the box. Right? If I color under this, right, it's not an infinite area. Right? This is a finite area. Right? So this may be a good wave function. Right? This is finite. And this is smooth. Right? So that might be a good wave function for us, right? It may look like that. You have kind of a sense of what the probability distribution or what the system should look like. And it can also look different. I mean, it could also look like this. This is another example. So it could look like that, but it also could change signs. Right? It could look like that instead. And there's nothing wrong with that. Right? It's still smooth. It still integrates to some finite value. Okay, so that's good. Nothing wrong with that. And so we might have, right, that kind of looks like a wave anyway, right? This kind of looks like a sine wave of a half period, and this looks like a sine wave of a whole period. Okay, totally reasonable. Right, but if we wanted to wager, hey, maybe our wave function looks like this, right? What if it looks instead, it starts to smooth, and then it drops hard to 0, 0, hard again, and then like this. Right? What if the wave function looked like that? Well, that's no good because it's not continuous, right? It's smooth, 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 smooth. Suddenly there's a point where the derivative doesn't exist anymore and it drops to 0, right? That's never going to work. Impossible. Right? So this is no good because of the discontinuities. Right? This is not smooth. Right? And I'll just give you one example at the end. Just kind of cram it down here at the bottom. It's not super important. It also couldn't look like this. Right? Because this may grow to infinity. As the box gets bigger and bigger, x squared, if you think it's looking like x squared, it's going to get bigger and bigger and bigger. Right? So the integral of this is not convergent. So as the length of the box, so if we define the length of the box to be L, as L goes to infinity, this is psi, the integral of psi squared goes to infinity. All right, so this isn't normalizable. All right, so this fails condition 1, which is that the integral must be finite. Okay, so we have a sense of what our wave functions must look like. Right, they have to be functions that are smooth and continuous, and they have to basically go to 0 at some point. Right? They have to eventually go to 0 at some distance, because otherwise the integral would never go to 0. Right? They have to eventually just kind of flatten out. Right? So that really gives us some limitations on what any particle in any box looks like. We have a very narrow range of functions that we can choose to represent our system, because there's only so many functions in the world that satisfy these equalities. Right? For instance, all of the polynomials, x squared, x cubed, x to the 4th, x to the 5th, x to the 6th, all the way up to infinity, don't work because they're not convergent. They integrate to infinity if the box goes to infinity. Right? So we're limited to certain functions. Right? That's really going to limit our approach. But that's also really helpful for us, because what that means is that systems that may physically give wave functions that look like this that are problematic aren't real physical systems. So it's not like we're going to hit a point in our calculations where we have systems that are in real life that are not continuously smooth. We're never going to have that problem because they're not real quantum mechanical systems. And so there's a correlation between what we can represent and what actually can be achievable in physical reality. And they're perfectly correlated in quantum mechanics. You can't write a smooth function for it. You can't create a real quantum system. So that really helps us kind of narrow down the kinds of things we need to look for. Okay. All right, so let's go to our second, let's go return back to where we left off last class, which is the second postulate, which are linear operators. I highly recommend, I'll just write a couple of sentences here about what a linear operator is. Remind you, I'll make sure to go back to your notes last class. We did talk a little bit about it, right? So for every measurement, every physical, observable, or measurement corresponds a linear operator that satisfies the following property. Let's say the following properties. So an operator, define O with a hat as a generic operator corresponding to a measurement, right? Like color or flavor. Right? These are the properties that it satisfies. One is that if you apply O to a wave function for that system, you get back a number. Just call it O sub n. Call this psi sub n. Psi sub n. Right? So you returns the original, right? Just like remember the color box in the homework. The color box in the homework, you've done it. We talked about when you put a white electron into the color box, you get a number out, which is what your readout is. Hey, I'm white. And you get the original white electron out. Okay, so I put in, this is my measurement, the O box. This is my operator. This is my measurement box. This is my input state. And I'm get out a number. This is my readout, the result of my experiment. And I get the original function. Okay, just like color, right? Remember the example that we did last week is that color is our operator, and we apply it on a wave function 1, 0, and we get +1 times 1, 0 out. Right? And this +1 means white. And of course, this is a white electron, and we get a white electron out. Right? And this is my operator. So an operator, which again, we really haven't quite figured out what exactly it is yet, but it's some mathematical function or some mathematical operation that we can do. That when we apply it to a wave function, it doesn't change the characteristic of the wave function at all. Wave function is unchanged, and we can factor a number out, this O sub n number. It's just a number. In fact, it has to be a real number, as we'll see. You get some real number out, and that's the measurement that you read out. Right? So if psi sub n is an electron that's white plus black, right? White plus black, and you measure the color of that electron white plus black, half the time you're going to get +1 out for white, and half the time you're going to get -1 out for black. right? That's your O sub n. So those are your, so O sub n. Just say, so let me give you some names for these things. These are labels that we'll use, notation. This, if this is true, we call psi n the eigenvector. An eigenvector of O. Eigen means same in German. I think I've mentioned that before. Right, so it's a vector that's unchanged, or some state that's unchanged upon a measurement or an operation. And O sub n is called the eigenvalue of O. Okay. And this is the one of the potential measurement results. So if we want to come up, so let's think about this, okay? In spectroscopy, I'm just going to pose a problem with you. In fact, we'll solve this problem. In spectroscopy, we want to measure the different energy levels of the molecule, right? We want to think about where the 1s orbital of hydrogen is relative to the 2s orbital. How much energy do you have to put in an electron to excite it? And we know that if you shine, and we'll see if you shine UV light at hydrogen, it absorbs some energy. It takes that 1s electron and excites it to the next state. It's about 160 nanometers in the blue. Right, so we know that there's some energy difference between these two states, the 1 and the 2 state, if you will, of hydrogen. What if we want to do a measurement of that energy? Right? We want to ask the molecule, hey, what are your energy levels? Well, we're going to have to define an operator for energy, a box that measures the energy. And then psi here, instead of it being in terms of color, the components of psi will be the different energy levels. Right? And there might be infinite energy levels. Right? That's why we might want to use a function here. Because a wave function, an atom doesn't have like color. Color is only 2 options. Energy, it has infinite options. It has as many options as you choose from. We'll have to talk about how many it has, but let's say feasibly it has infinite. Right? And so the idea is that we need to create a box that when we read in our wave function, it spits out one of the possible energy levels for the system times the original molecule. Okay, so we're just measuring the energy levels of that molecule. So we'll have to define an operator for energy. We'll be able to do that actually probably today. And the goal is that we choose the operator in the wave function such that when we pick the right representation of our system psi, and we choose an operator, a box, we build a box, then we're guaranteed that if we build everything correctly, that every time we measure a system that we can measure the energy of, we'll get an energy value out, the eigenvalue for the energy, times the original function. Just like color. Same idea, same concept. We want to, measurements are operations that we do on systems that leave them unchanged. Right? It's not a manipulation, but a measurement. Measurement means it's unchanged. Right? So the wave function n is the wave function out. So we have to construct that energy operator, and we're not that far from doing that. So let's go back to that. At the end of last class, I had this table of operators, and I stopped it halfway. So let's go back and continue that and look at it a little more carefully. And we'll do some examples. All right, so some examples of operators. All right, well, first we want to think about what we want to measure. Right, so let's pick our measurable. Right, just something we can measure about an object. We're going to pick a symbol for it, like some symbol for that measurement. And then the operator. Right, and if you remember from last class what an operator was, an operator is just a mathematical operation. The plus sign, the sum, is an operator that takes in 2 numbers and gives you the sum. Minus sign is an operator that takes in two numbers and gives you a minus. The derivative operator is an operator that takes a function and gives you the derivative of the operator, and so on. So you can think of multiplication as by a number as an operator. You take in a value x, and you have a multiplication operator that takes in a real number a and a number x, a variable x, and it returns x times a. Multiply. So you can think of this I'm just formalizing very, very simple mathematics, right? So we have an operator for every, right? So if our measurables are sums of particles, we have a plus operator. Turns out it's not a real operator in quantum mechanics. We can think of that, right? Maybe we want to subtract things, maybe we want to multiply things, right? We're going to have operators for these. But of course, we're thinking of physical objects. We should ask them, you can't really add two electrons together, right? That's not really reasonable. So what are some things that we can measure about a particle? Well, obviously, the first thing we should ask is position. And we talked about this in depth last class. Right? And I'm going to label, usually I'll label things as X, Y, and Z. Sometimes I'll label them as R if I want to keep things generic. And maybe I want to think about the X position, Y position, and Z position. The operator is just the label. It's just the function X. So if I want to measure the position of X, I know this seems very weird, but we'll prove that this works. What this means is, let me just do an example here. If I want to measure the position of an object that has, let's say, three possible positions to begin. All right, we have a little box that has three detectors. All right, we want to ask the probability. Okay. So we have let's just say we have a box here with detectors X1, X2, and X3. All right, and the counts, the number of times that the idea is, again, if we measure particles with these detectors over a long time, we can measure the counts of how many times those detectors click, where the particle moves over it. So we're going to have some measurements, some statistics like this, right? These are the counts of detections. It's a small text, I'm sorry. And the Y values of these, which I'll mark in blue, that's the right? This is the probability of finding the particle at position X2. So the Y value of this is the square of the wave function at that position. And this would be the square of the wave function evaluated at this position. We saw that last class that the square of the wave function tells you about the probability. All right, so let's apply a measurement of X to this state. All right, so psi for this state is just going to be a vector of three positions, where the first component is psi evaluated at X1, psi evaluated at X2, and psi evaluated at X3. And again, those are just the square roots of the numbers that you measure here. Right? So we just have to measure the counts and square root them, and those are the coefficients on our wave function. Right? Because they tell us something about the probabilities. And so if we apply X to psi here, it's going to return one of three values. What's it going to return? Well, at psi squared of X1 time probability, it's going to return X1. So let me just write this. So we're going to have three potential answers from our box. What's it going to return? Well, one, it might return the position at X1. Maybe the particle is at X1 when we measure it. So it's going to return X1 times the wave function. Right? This is if the particle we measure and it's at X1. It's going to return X1, and it will do it at the probability psi squared X1. So the probability P is just psi squared X1, right? The number of counts. And then maybe sometimes it'll return the function, the particle again times x2. And it's going to do that at probability psi squared of x2, right, from our statistics. Or it's going to return the position 3 times our wave function with probability equal to psi squared at x3, right? And these probabilities, right, they just come from our statistics. Right? They just tell you how likely it's going to be at one of the positions. They can all be the same. They can be slightly different. Who knows? It doesn't matter. We can certainly figure it out if we write down a system in our box and do the math. We can figure out what all the psi's are. It's no problem. We could go measure it. Doesn't matter. But we know that for a fact that these are telling us that these are the probabilities of seeing each one, the particle at each of those positions. And so when we apply our operator x on psi, it's going to return the value of x we see the particle at times the original function at these probabilities. You only get one at a time. Go ahead.
I don't know why, but I'm still like confused on like how you're saying it's the probabilities, but then psi squared times like.
No, this is psi squared evaluated at x of 1. This is psi of x of 1 all squared. Would it be better if I wrote it like this instead?
Okay, that makes sense to me.
Maybe if I wrote it instead like this instead. Would that be better?
It's
Yeah. So it's the value of it's the y value of psi evaluated at x1, this value squared. Right? And that's the probability. Anytime you see psi of x, think a function, not psi times x. Now here, x is being multiplied. It's actually a number that you get out, right? It's the readout. All right, we'll see how this works in a little bit, right? We can take averages over this, right? Imagine that again, you can ask an average, right? Sometimes it's at x1, x2, or x3. You could ask a question, what's the average position you're at? We'll come up with a formula to calculate averages next class. We can do statistics on this. Now, I'm going to show you another operator that we need to think about for energy. And it's going to have a form, the operator, that makes no sense. I wrote it down last class and I stopped, which was really unfortunate. I want you to accept this formula as it is, and we'll see later on, once we build up a little bit more rules, why it is what it is. Not quite, it's kind of hard to explain this, so I have to kind of use circular logic to come back and understand the form of this. It's a very strange formula, but it's super important. And the next one is momentum. Momentum is related to energy. And I'll show you that very soon. Right? And momentum is very useful. We want to think about things that are conserved. Right? So that means we need to think about things that we can measure that are true everywhere and at all times. And so momentum is something that's conserved in space and in motion. So the idea is that imagine I have two particles coming together on a, this is the very Einsteinian way of thinking about things. Imagine I have a train car, right, with two particles of a lab set up on a train car where two particles are being collided together. We have a particle collider on a train. Okay, and you're on the train, standing next to the particle collider, watching the particles hit each other and bounce off. Right, you're tracking them with your X position meter and your stopwatch, and measuring how the particles scatter off of each other. Okay, and you measure that they come in with some momentum, and they come out with some momentum, and that momentum is conserved. Right, the momenta in are the same as the momenta out. Conservation of momentum. All right. Now, what happens if I'm instead at a train station and watching this particle move by? Right, so now I'm not on the train moving at the same rate as the accelerator, but now I'm watching the accelerator move in front of me and I'm stationary. Right, what's going to happen? Well, I'm going to see the particles from my perspective move differently. Right? It's kind of hard to see that, but it's a classic Einstein argument that the trajectories of the particles from my point of view on this moving frame of reference looks different from my goggles or my track than it does if I were to stand at the same place in the train car and move along with the particle accelerator. Right, so the positions look different because everything's moving. But I go in, well, now I'm on the train station, I can still measure the momenta. So I'm on the train station, I'm measuring the momenta of all the particles, right? M times V, the velocities and the masses of all the particles, adding them all up, and I find that all the momenta are conserved too. I get the same momentum that me standing in the car get. So it doesn't matter from which perspective I look at, no matter what, momentum is always conserved and always has the same values. They always conserve. So the momenta into a collision or the momenta out. That's always conserved. So velocities will not be conserved because a particle moving on a moving frame of reference looks slower than a particle in a stationary frame of reference moving. Right? Think about how fast a car looks like when it's moving 60 miles per hour relative to you when you're standing still versus a car moving next to you while you're also going 60 miles per hour. The relative velocity you see has changed, but the momentum is still the same. So we're going to use momentum in this class when we talk about motion because it's conserved and we can look at it from any perspective. Right? And momentum is P. Let me get rid of that hat. It's a vector, so it has three directions. Right? And I might call it Px, Py, and Pc. All right, it's a vector. Remember, it's m times v, but m's the v's and velocity. That's how Pavlovsky would teach it to you. The operator, however, does not look like that at all. It has a very strange behavior, a very strange formula. It's I times h over 2 pi. H is a number which I haven't defined yet, but we will soon, times the derivative. So to measure the momentum of a particle, I take the derivative of the wave function, and I get those same wave function out. Right? So what this is saying is that if I apply, this is p sub x to psi, I get minus I h over 2 pi. I'll give you a value for h in a second. We'll talk about h really quickly. Times the derivative of the wave function with respect to the position. And this is going to give me some number. Let's just call it p sub x times psi, where p sub x is a number. So this is crazy, right? So what this is telling me is that if I have a system that has a well-defined momentum, it's a function whose derivative is equal to itself. That's obviously a limitation. Now, very few functions have a derivative equal to itself. Okay, so this really limits the kind of functions here. Let's come back to this h in just a second. So I'm going to save it for next class. We'll come back to this next time. This is a number for next time. Right? We will define this number exactly. Right? It's just, remember, it's a special number. All right, so the weird thing about the momentum is that it's imaginary too. There's an I in here. Right? It's a very strange concept. Well, why is it imaginary? Well, once again, we understand this thing about waves and that they're complex, right? You have this transverse and this longitudinal behavior that's complex. And so if we have a particle that's real in position, right? I can measure its position at every point. Right? I know exactly where it is. What that means is that my momentum is imaginary. Now, what does that mean? Well, if the momentum is imaginary, that means it acts like a wave. And so if you have a particle that has a defined position, your momentum is undefined up to a phase of 2 pi in a complex plane. It has some oscillatory behavior. Momentum has an oscillatory behavior. What that means is that if your position is exact, your momentum is undefined on some circle, which means that there is no defined momentum. It could be anything. Okay? So defined position means undefined momentum, and it turns out vice versa. Now, we don't have the rules yet to understand why this is, but this is built into the laws of quantum mechanics. That if you know position exactly, momentum is completely undefined. So a particle, what that means is that a particle that's, if I could say, for instance, a particle is exactly at this point right here, localized right at this corner to exact precision, zero uncertainty, it's exactly right there, it has all possible momentum, which means it could be moving at any energy, any rate, any direction. Completely undefined. And vice versa. If I could catch a particle moving with a speedometer, with a speed radar, and say, hey, it's going this fast, I don't have any concept of its position either, right? Remember, this is the same behavior we see with color and flavor. If I know the color exactly, I don't know the flavor at all, and vice versa. These work exactly the same way. If momentum is defined in real, position is defined in real, momentum is undefined and imaginary. Just like color and flavor. We'll see more of that as we go through it, but just to keep that in mind. All right, let me just write one more and then we'll talk about it and do a quick solution here. So we have position and momentum, all right? We can have all the rules now. We can build operators with position and momentum operators. So for instance, we can measure x squared or p squared. Nothing wrong with that. We can measure p twice. That would be p times p, that's p squared. So we can measure squares of things. We can measure different types of properties with these. We can construct new operators of momentum and position. So let's do that for energy really quickly. Two different types of energy. Let's do kinetic energy. Right, the label that I will use for kinetic energy is T. Right, for kinetic energy. Right? And let me just write down here at the bottom, let's just do a little bit of math. So classically, T is 1/2 times the mass times the velocity squared. Right, you guys remember this? 1/2 v squared. But as I said, velocities are not very useful for us in this class because velocities aren't conserved. Velocity from a moving observer looks different than a velocity from a stationary observer. We'll use momentum instead, right? Momentum is m times v. So maybe we can sub in momentum here. Right? P is equal to mv. Right? So we could take these two equations and put them together. Right? And we find some really nice. We find that T is equal to p squared over 2m. Right? So the kinetic energy of the system is the square of the momentum times divided by 2 times the mass. Well, we have an operator for momentum. Right? So we can promote it. Right? We can say, okay, let's say we have operators now. We have a box, a p box. We can measure p twice. It'll be p times p, that'd be p squared. Measure p twice with our momentum box that we've constructed. And if we measure it twice and divide by 2 times the mass, we're measuring the kinetic energy. That's all it is, just by definition. So let's plug in our value for momentum here. Right, so this is going to be IH over 2 pi d by dx squared over 2m. All right, so let's just kind of work this out. Minus I squared is 1. Sorry, no, it's not. Okay, I squared is minus 1. Minus 1 is plus 1. All right, so we have a plus. The I goes away. That's good. Right, so p squared is real. The I is gone. So we can measure maybe we can measure the magnitude of the momentum. We lose something about the direction, but maybe we can do the magnitude. We get an h over 2 pi squared. So I'll just write that here. And this is all divided by 2m. And then we have the derivative squared. We can write this as the derivative of the derivative, right? It's 2 p operators, right? This is the same as p times p. Right? So this turns out to be the second derivative operator. The derivative of the derivative is the second derivative. And I'm just doing it with relative to one direction x. All right, so I can simplify all of that. And what I get is that T is h bar. Oh, sorry, no, don't do that. Sorry, that's my bad. We haven't introduced h bar yet. H over 2 pi squared times 1 over 2 times the mass of the particle times the second derivative of the function. And so we have this equation that's got some numbers and a second derivative. So in just the last 30 seconds, let's just set up a problem. Right? Imagine we have a particle that just has kinetic energy. We'll finish this up next class, but let me just set it up for you. Right, we're going to have that every system that satisfies the measurement of kinetic energy is going to give some kinetic energy value T sub E times psi. And that means minus h over 2 pi squared times 1 over the 2 times the mass of the particle times the second derivative of the wave function gives me the wave function back times a number. Right, so this means that psi must be basically the same as the second derivative of psi up to a constant. So already we have a very stringent limitation of what we can measure for kinetic energy. It has to be something that can be represented by a function that when I take two derivatives of it, I get the same function back times a number. Very, very few functions in the universe gives you this behavior, right? When you take the second derivative of the function, you get the same function back, right? So we'll solve this next class, right? It's very easy to solve this. There's only a couple of options. And we're going to see an equation that we've already seen before. Well, and then we'll interpret this physically. We'll ask what the energy of this particle is. T sub E, what's the kinetic energy of this particle? What's the wave function of this particle? And what does it look like? All right, so we're almost there. This is our first quantum mechanical problem. Something that has just kinetic energy on it. And it needs to be represented by something whose function is the same as the second derivative. All right, guys, have a good one. We'll come back to this.